Hello, so this is my protein assignment in comparison to my other protein assignment. I had accidentally did the Acetylcholinesterase, and when I was assigned to collagen, so instead of choosing a partner, although I did talk to other people with the same protein, I kind of just did myself since I have the same protein. And this was the model that I did. And one of the resources I found through the links provided, it was a bunch of different squigglies and everything, because I noticed that there was a bunch of different ways that you could articulate the design. And what I thought was pretty was just the squigglies, and this is 3D because it's not paper. It's not like just flat. It's taped onto a piece of paper that kind of like pops out at you, because it's not one type of way. And there's it's not attached to each other. There's like squigglies like all around. And that just goes to show how complex it is. And then up here, it's where I kind of found it from. Just the processing of it. Through the equation, and then I put enzymatic hydrolysis of ACH by AcHE. So yeah. Then, in comparison, this assigned protein and mutation is Acetylcholinesterase, and the mutation is sarin toxin interaction. The normal function for this protein is enzyme, and I know this because it is a primary role to catalyze the hydrolysis of acetylcholine, and this function is crucial for the nerve activity or the termination of signals, which differs from the one I had previously, which was collagen, because the structure protein for collagen, the normal function for collagen is structural. When compared to AcHE, it's enzymatic. And I knew it was structural because it had nothing involving with enzymatic activity, and it focused on maintaining the shape and the physical properties of the connective tissues. So yeah. For AcHE, it is normally found, the subcellular location is the synaptic clefts of neurons, particularly in the post-symptomatic membrane or attached cell membranes at the synapse, or it can be found in red blood cells, although in smaller amounts. When compared for collagen, you can find it pretty much inside the ECM, the extracellular matrix. The types of cells that contain this protein for AcHE, it's found in animals, especially in vertebrates and invertebrates, since it's a neurotransmitter in animal cells, but you will not find it in plants. And then for collagen, it's pretty much the same thing. To characterize the mutation for ACE, I have put, or my partner had put, if the mutation decreases the enzyme catalytic efficiency, it may lead to a prolonged acetylcholine activity in synaptic clefts, resulting in overstimulation of the postsynaptic cells. And then if the protein, we're supposed to do one. I did all three. Okay. And then afterward, for the change in mutation, I had just wrote the same one, just a substitution of a glycine for a larger amino acid would disrupt the triple helix formation. So yeah. a little different, but that's just because we're talking about different situations occurring. Another thing I had added about the AcHE is serin toxin binds to the active state of AcHE, leading to the chemical modification of the enzyme rather than the chemical genetic mutation. This interaction of serin with AcHE has a profound effect on this protein's structure and function. So that kind of relates to what it has to do about the structure, just like collagen has to do with structure. For the assigned mutation, first I choose serine. The chain of serine consists of a hydroxyl group attached to the methylene CH2, making it a hydroxyl-containing amino acid. This is polar, it is neutral, and it is small compared to the other 19 AAs. The different interactions that the original AAs can participate in is hydrogen bonding and covalent bonding. This is kind of similar to collagen because collagen can also include serine as a mutation, which I also did use for my mutated ion, which included the same pretty much information. The difference I wrote was the substitution in glycine with serine, and type 1 collagen disrupts the collagen triple helix structure. And I just put more into that. So it's interesting how serine could work with these different things, with these different proteins, and just create different effects to each one. And then for the mutated amino acid, I had talked about serin toxin and its binding to AcHE, which was polar, negatively charged, and the phosphorylated side chain is significantly larger than the serine side chain, which is what it is compared to the other AAs, amino acids. And then the difference inside the types of interactions that the mutated amino acid side chain can participate in compared to the original amino acid is just basically the effect on proteins. So the irreversible inhibition, which is the binding of serin to the active site, resolves in an irreversible phosphorylation of the serine residue, essentially, and then the loss of catalytic activity. Without the ability to break down acetylcholine, the enzyme cannot regulate the neurotransmitter effectively. And then, how does your mutated affect the protein function? It affects the protein function cellularly because when the accumulation of acetylcholine, when AcHE is inhibited by serin, it can lead to an overstimulation of neurons, muscle paralysis, respiratory failure, and prolonged stimulation of neurons and muscle cells, or organismal function. And that way, it can lead to toxicity and death. Because serin poisoning leads to a widespread toxicity throughout the nervous system and can be lethal without prompt treatment. And yeah, which and relates to collagen. The things we have to worry about were pretty much osteogenesis imperfecta, which is brittle bone disease, fragile skin, joint issues, and other severe complications that has to do with collagen. So that's my comparison on the two different proteins, and thank you.